So good morning, everybody. Today we're going to go over magnets one more time. I know y'all have already been going over magnets every day this week. Hopefully you've been watching the videos, especially the Bill Nye video yesterday. Today I'm just going to go over a couple of things, and then you do have an assignment for magnets. This assignment is going to be treated like a quiz. You do only have 2 attempts, and then you are not allowed to see your results after you are done. So please let me know if you have any questions before you take your second attempt. So a magnet is an object that produces fields that attract or repel other objects. Hopefully you've seen magnets before. They're on your refrigerators. Sometimes you can buy little Connect toys that kind of join together. Those are magnets. Does anybody not know what a magnet is? All right, good. So first we're going to start off with magnetic poles, and there are 2 types of poles, the north end and the south end. And again, this is what we call North Pole and the South Pole. These are the electrical forces, or the regions that produce electrical charges that cause the magnetism. And opposites attract, just like we've been talking about before with forces. Magnets do exert forces on each other. The opposite ends are going to attract each other. So the north's going to pull towards the south, and the south's going to pull towards the north. This is whenever you put 2 magnets close together and they slam shut. Like poles are going to repel. So if you've ever flipped a magnet backwards and tried to force it together, you kind of can't push it all the way close. And that's because they're the same poles. They're not going to go towards each other if they are the same. And I really wish we had magnets so that way y'all could play with them. But y'all aren't allowed to touch anything here in school. If you have magnets at home, go ahead and try it. Put them close together. You're going to see them attach. Flip one of the magnets, and you're going to see it not attach. It's going to be pushing away, sort of. So no matter what you do to a magnet, it's always going to have a north pole and a south pole. That's just how magnets work. They always have to have each pole. If they don't have those poles, well, they're not a magnet. So if you continuously break a magnet in half, it's still going to have a north end and a south end. Again, no matter how many times you break apart a magnet into however many pieces you want, it's still going to have a north side and it's still going to have a south side. Magnets, again, do have forces, and those forces are going to create field lines. These are pieces of iron filings around bar magnets. Mr. Waller showed you this in a video. Hopefully you watched that. So these field lines are caused by electric charges, and the strength of interaction is going to depend on how far apart they are or how close they are. Again, this causes magnetic fields, and you can see the field lines, the shapes, the patterns that surround the magnet. So again, this is from the video.
Make sure to observe the pattern both overhead and from the side. From the side, you'll observe that the field is 3-dimensional, meaning the magnetic field extends in all directions from the North Pole and wraps back around to the South Pole.
Okay, so this is explaining that the field lines don't go side to side. They don't go left to right. It's not 2-dimensional. It's 3-dimensional. So it rotates all around just like a ball. That's what the field line does. Again, it's not 2D, it's not flat, but it's 3D. It goes all around just like a ball. No. Okay. So again, these are the magnetic field lines drawn out instead of the iron filings. It's going to be strongest inside the magnet, which makes sense because the bar magnet is the strongest magnet. So everything inside is going to be the strongest field lines. Again, you can see that it's stronger at the poles, the north end and the south end. As it extends out, it starts to become weaker. And you can tell it's weaker because the lines are more spread out. Remember, when they're close to each other, they're stronger. And as they spread out, they get weaker. The magnetic field lines are always going to leave the north end, and they're always going to go towards the south end. Again, you can see how the field lines interact with each other. These are opposite poles, and you can see the field lines connecting from the north to the south, from the south to the north. These are attracting each other. These are opposite poles from the north to the north, and you can see how they're pushing away from each other. It's kind of really hard to see, though. That's why we like to draw on. Like I said, it's always going to leave the north end and go towards the south end, just like electric currents. So what makes a metal magnetic? Well, most objects you have are not magnetic, and that's because they have atoms, and those atoms have electrons, and those electrons spin in crazy directions. It's all random. They don't have any order to them, and because of that, nothing is really magnetic, except for very few materials. And that's because electrons in magnets don't spin in random orders. Instead, they all conform to a same rotation. So they all start spinning in the same direction. They're all going to have that same flow. They're going to produce that tiny current since they're all going in the same direction. And then they're going to make the object become a magnet. So it's kind of like when you're swimming in a pool with friends, a circle pool. And y'all are all just playing around, having fun most of the time. But then all of a sudden you decide to go around in a circle in the pool. Have y'all ever tried that? Well, if you ever do try it, going around in a circle, you and your friends over and over and over again, what do you think that's going to do to your pool?
Create a whirlpool.
It's going to what?
It's gonna create a whirlpool.
It's going to create a whirlpool.
You're gonna get sucked down to the bottom.
That's exactly what's going to happen. If you haven't tried that before, try it. It's really fun. The little kids get stuck floating and they can't swim to save their lives. It's pretty funny. Anyways, so that's what these electrons are doing. They're all starting to spin together.
Someone get a really big mixer. Get a really big mixer and just.
Exactly, that's a mixer. Just you and your friends will be a giant mixer. Well, anyways, all the electrons are still spinning in the same direction, and that's going to create a current, and that's going to turn the materials into magnets. But it doesn't happen for all types of materials, only certain materials. And it's only going to happen to the materials that have magnetic domains, and these are clusters of aligned atoms. Sometimes they're not going to be lined up, which means they're partially magnetic. And then at times they're all going to be lined up, which means they're really magnetic. And the only materials that can be like this are going to be iron, cobalt, and nickel. And we call those ferromagnets because they can become magnetized. Think about when you have a bunch of iron nails. You have a pile of them. If you've ever worked on any woodwork, you have iron nails. They're not magnetic at all. But when you put them near a magnet, they instantly attach to that magnet. They become magnetized. I don't remember in the video, did he show you materials that were magnet and were not?
In the Bill Nye video, yes.
Okay, in the Bill Nye video, yes, but not in Wilson's video. Okay, well, that's fine. And that video with the Bill Nye, it does show you that not everything can be a magnet. The only objects that are attracted to magnets are these three types of materials right here, iron, cobalt, and nickel. And that's because these are the only ones with domains that can actually become aligned and can actually become magnets. So again, iron, nickel, and cobalt. So we have two types of magnets called temporary and permanent, and they're exactly what they sound like. Temporary magnets are magnets that are only aligned for a short time. Just like whenever you have a magnet in your paper clips, the paper clip near the magnet is going to start attracting other paper clips. But as soon as you remove that magnet, the paper clips just fall down. They're no longer magnetized. Then we have permanent magnets, and these are magnets that can become aligned for a long period of time. And these are the magnets that you have on your refrigerators. You can even create them by stroking a bar magnet with these ferromagnets. The more you stroke it, the more aligned it's going to be, and the more permanent it will be aligned for. You could also demagnetize magnets, meaning you can take away their magnetism. Don't ever do this to your refrigerator magnets. Your mom would be mad. But if you keep dropping magnets down, they're going to lose their alignment, because as you drop them, you're making those electrons get out of order, get out of sync. Well, obviously the same thing happens when you hit it over and over again. You're making those electrons stop moving in the same direction because, well, you're hitting them. You could also do it by heating. When you're heating objects, those electrons start spinning faster. They start getting more chaotic. They start getting out of alignment. By keeping the like poles together, so if you put north and north, south and south, they're going to be pushing apart so much that they're going to start to get weaker and weaker and weaker. The world's largest magnet is, well, Earth. The Earth has a north pole and the Earth has a south pole, and that's how we rotate around those axes. And that's why Earth is the strongest magnet. And it's because of inside the core, we have materials like iron, nickel, and cobalt who are constantly spinning or constantly moving, and that's creating the magnetic field. This just talks about how the poles are going to end up switching one day. It happens every, what, a million years? The North Pole becomes the South Pole and the South Pole becomes the North Pole. We don't have nothing to worry about in this.
We're going to be long dead by then.
Yeah, we'll be long. And it happens so slowly that you don't even notice it. Like, you won't. The only way you'll notice it is that in a million years, the compass is pointing the wrong direction. That's how you'll be able to notice it.
That depends if you're alive a million years.
Yeah, exactly. So bar magnets do act like a compass. That's why compasses point to the north, because, well, Earth's a big giant magnet. These just talk about other magnets, electromagnets. This is whenever you plug in a magnet. I'm sorry, this is when you plug in a metal to a battery, it creates a magnet. I think they talked about all this before, though. Remote controlled door locking mechanisms.
I talked about that.
Generators.
He did talk about that.
Well, generators are awesome. This is what Tesla invented. These are giant magnets that just spin and spin, and because, well, they're permanent magnets, they constantly spin forever and ever, and they constantly create energy forever and ever. If you look online, these magnetic generators cost a lot more money because they last forever. You don't even need to put gas in them. Door sensors for homes, they use magnets. Anytime you open a door, the magnet becomes a part, the alarm rings. Credit cards have magnets. Those black strips are magnetic strips. Magnets in landfills, that's how we recycle objects. We have a giant magnet that hovers over the trash and it picks up all the material that can be reused, like the iron, nickel, and cobalt. And trains. Trains are starting to use magnets at the bottom. They're opposite, no, not opposite. That would make it close.
Same.
They're the same poles at the bottom of the train. So it kind of causes it to hover. I'm not saying hover like a foot above. I'm saying hover like a centimeter.
I heard a millimeter.
Is it a millimeter?
No, I'm just saying like a millimeter.
Yeah, it's like a millimeter. It's so small, but think about it. You have a big old heavy train pushing down on a rail. If you even raise it just the slightest, it's going to cause less friction, and we're going to have these trains going like 200 miles per hour. Bullet trains, that's what we call them. Not 200 miles per hour. I'm exaggerating, obviously. But hopefully one day soon.
500.
Hopefully one day soon, San Antonio can build a bullet train to Austin so we can get rid of all that traffic. That's crazy. Keys also use magnets, and that's it. Oh, we're not doing a lab today. Sorry. We're doing an assignment. We did do the lab. Okay, so go ahead and do your assignment. Again, you only have 2 attempts. It is like a quiz. You can't see your results at the end. So if you have any questions, let me know. If you have any other questions about anything else, stay on. If not, you're free to go.